Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This video on the integration of rational functions using partial fractions is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. In this video, we will integrate a proper rational function whose denominator contains only distinct linear factors, integrate a proper rational function whose denominator contains a repeated linear factor, integrate a proper rational function whose denominator contains a distinct irreducible quadratic function, and integrate a proper rational function whose denominator contains a repeated irreducible quadratic function. If the denominator q contains only distinct linear factors, then p over q can be written as p of x over q of x, which we can write as equal to the sum of a sub 1 over x minus a sub 1, plus a sub 2 over x minus a sub 2, and so on, including a sub n over x minus a sub n. In this case, the integral of p of x over q of x is equal to the sum of the integrals of each of the individual terms, where a sub 1, a sub 2, and so on, including a sub n, are real numbers. In this case, since the denominator contains linear factors, to maintain the terms as proper fractions, the deconstructed numerators will be made up of only real numbers. As an example, let's solve the integral dx over x minus 2 times x plus 1. We isolate the integrand and deconstruct it using a over x minus 2 plus b over x plus 1. At this point, the original denominator becomes the common denominator for the deconstructed terms. Next, we clear the fraction by multiplying this common denominator through to get 1 equal to a times x plus 1 plus b times x minus 2. Distribute to get ax plus a plus bx minus 2b. Group the x terms, then factor to get a plus b times x. Here we must equate the coefficients with the like powers of x. Since there is no x term in the original numerator, a plus b will equal 0. 1 is an integer term in the original numerator, so a minus 2b will equal 1. We solve this by substitution. A equals minus b, then substitute minus b for a in the other equation. Add the like terms to get negative 3b equals 1, or b equals negative 1/3. Replace negative 1/3 in the original equation to get a equals 1/3. The deconstructed integrand will then be 1 over 3 all over x minus 2 minus 1 over 3 all over x plus 1. We now use this in the integral. We then split the integral and pull out the 1/3 as constants. This gives us 1/3 times the integral of dx over x minus 2 minus 1/3 times the integral of dx over x plus 1. Take the integrals to give us our final answer, 1/3 times the natural log of the absolute value of x minus 2 minus 1/3 times the natural log of the absolute value of x plus 1 plus c. If the denominator q has a repeated factor x minus a to the n for n greater than or equal to 2, an integer, then the decomposition of p over q includes the terms a sub 1 over x minus a sub 2 over x minus a squared, and so on until a sub n over x minus a to the n, where a sub 1, a sub 2, and so on, including a sub n, are real numbers. Like the last form, the denominator is made up of linear factors, therefore the numerator must be real numbers. As an example, let's take the integral of x squared over x minus 2 times x minus 1 quantity squared. To deconstruct the integral, we set the integrand equal to a over x minus 2 plus b over x minus 1 plus c over x minus 1 quantity squared. When we multiply through the common denominator, we get x squared equals a times x minus 1 quantity squared plus b times x minus 2 times x minus 1 plus c times x minus 2. FOIL the binomials to get a times the quantity of x squared minus 2x plus 1 plus b times the quantity of x squared minus 3x plus 2 plus c times x minus 2. Distribute the parentheses, then group the like terms. We can now factor the x variables to get a plus b times x squared plus negative 2a minus 3b plus c times x plus a plus 2b minus 2c. Since the original numerator only has a single x squared term with a coefficient of 1, a plus b equals 1. With no x term, negative 2a minus 3b plus c equals 0, and with no integer term, a plus 2b minus 2c equals 0. In the first equation, we solve for b, then substitute 1 minus a into the second and third equations. These simplify to a plus c equals 3, and negative a minus 2c equals negative 2. Solve for c in the second equation and substitute 3 minus a into the third equation. This simplifies to a minus 6 equals negative 2, or a equals 4. Take this to the first equation to get b equals negative 3, and into the second equation to get c equals negative 1. Our new deconstructed integral is 4 over x minus 2 minus 3 over x minus 1 minus 1 over x minus 1 quantity squared. We can then separate the integrals and move the constants outside the integral sign. 4 times the integral of 1 over x minus 2 equals 4 times the natural log of the absolute value of x minus 2. Negative 3 times the integral of 1 over x minus 1 equals negative 3 times the natural log of the absolute value of x minus 1. And the integral of 1 over x minus 1 quantity squared is 1 over x minus 1. We then add the plus c. If the denominator q contains a non-repeated quadratic factor ax squared plus bx plus c, then the decomposition of p over q includes the term ax plus b over ax squared plus bx plus c, where a and b are real numbers. Since this form includes a squared term in the denominator, a proper fraction will therefore be possible with a first degree x term in the numerator. As an example, let's solve the integral dx over x times the quantity of x squared plus 1. We first deconstruct the integrand by making it equal to a over x plus bx plus c over x squared plus 1. Multiply through the common denominator to get a times x squared plus 1 plus x times bx plus c equals 1. Distribute to get ax squared plus a plus bx squared plus cx equals 1. Group our like terms and factor the variables to get a plus b times x squared plus cx plus a equals 1. Looking at the groups individually, a plus b equals 0, c equals 0, and a equals 1. This means b must equal negative 1. Use the new integrand with the computed values to get the integral of 1 over x plus negative x plus 0 over x squared plus 1 dx. We then split the integral into the integral of 1 over x dx minus the integral of x over x squared plus 1 dx. The integral of 1 over x is the natural log of the absolute value of x. For the second integral, we use substitution. Let u equal x squared plus 1. Du will then equal 2x dx. To match our integrand, x dx equals du over 2. Substitute to get the integral of du over 2u. Move the 1/2 outside the integral as constant. The integral of du over u is the natural log of the absolute value of u. Replace the u to get our final answer, natural log of the absolute value of x minus 1/2 the natural log of the absolute value of x squared plus 1 plus c. If the denominator q contains a repeated irreducible quadratic polynomial, the quantity of x squared plus bx plus c to the power of n, for n greater than or equal to 2, an integer, then the decomposition of p over q includes the terms a sub 1 times x plus b sub 1 over x squared plus bx plus c, a sub 2 times x plus b sub 2 over the quantity of x squared plus bx plus c squared, and so on, including a sub n times x plus b sub n over the quantity of x squared plus bx plus c to the n power, where a sub 1, b sub 1, a sub 2, b sub 2, and so on, including a sub n and b sub n, are real numbers. Like the last form, with a second degree variable in the denominator, it is possible to have a first degree variable in the numerator. As an example, let's solve the integral x cubed over x squared plus 16 quantity cubed. We first deconstruct the integrand into ax plus b over x squared plus 16 plus cx plus d over x squared plus 16 quantity squared plus ex plus f over x squared plus 16 quantity cubed. This makes x cubed equal to ax plus b times x squared plus 16 quantity squared plus cx plus d times x squared plus 16 plus ex plus f. When we complete the multiplication on the binomials, we get ax to the fifth plus bx to the fourth plus 32ax cubed plus cx cubed plus 32bx squared plus dx squared plus 256ax plus 16cx plus ex plus 256b plus 16d plus f. Note that there is only one term containing an x to the fifth and one term containing an x to the fourth. Since this is equal to x cubed, that means a and b must equal 0. This means we can eliminate every term that contains an a or b variable, leaving us with x cubed equals cx cubed plus dx squared plus 16cx plus ex plus 16d plus f. Notice that there is only one x cubed term. This means c must equal 1. Also note that there is only one x squared term. This means d must equal 0. Fill in the value for c and cancel the d terms, and we are left with x cubed equals x cubed plus 16x minus ex plus f. We then factor the x. Since we have accounted for the x cubed term, the remaining ones must equal 0. F equals 0, and 16 minus e equals 0, so e equals negative 16. We then fill in our values to the deconstructed integrand. When we eliminate the 0 terms, we are left with x over x squared plus 16 quantity squared plus negative 16x over x squared plus 16 quantity cubed. We then use this to replace the original integral. At this point, we can separate our integrals and move the negative 16 outside the second integral as constant. Next, we use u substitution. Let u equal x squared plus 16. Du will then be 2x dx, and x dx equals du over 2. Substitute to get the integral of 1 over 2u squared du minus 16 times the integral of 1 over 2u cubed du. Move the 1/2s outside the integral as constants. 1/2 of 16 is 8. Next, let's express exponents as negative exponents and complete the integrals. The integral of u to the negative 2 du is negative u to the negative 1. The integral of u to the negative 3 is u to the negative 2 over negative 2. Simplify to get negative 1 over 2u plus 4 over u squared. Replace the substituted u to get the final answer, negative 1 over 2 times x squared plus 16 plus 4 over x squared plus 16 quantity squared plus c. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you and good luck with your studies.